discussion for today. Share. All right. All right, can you see the slides on the screen? Okay, good. Let's discuss this first before we move on with our SCED process, yeah. Okay, we have discussed a little bit about the litho process last week, and let's just do some recap in the form of this exercise or discussion, if you like. Okay, so look at the structures below in the picture. So let's discuss on how to print these nanopillars on silicon. So on silicon here means oxide on silicon, because we have oxide before silicon during the lithography process. So how do we do the printing? Suggest your photoresist and reticle or mask that you need to use during the process. Okay. Suggest photoresist and reticle mask to be used. So here when the question requested for a suggestion, so that means either the type is actually meant for the type of the resist, positive and negative, and then dark field, clear field for the mask. All right, anyone would like to share your suggestion? So you can see nanopillars here printed after the CAD process. So anyone would like to give a suggestion? If you are the process engineer, how would you suggest? Anyone? Tak ada ke? Let's go for Nuraihan. Nuraihan Shamimi. Raihan, any suggestion? How do you want to print this? You can unmute yourself and write down as well. Come on. Okay, let's go with this. I think negative photoresist with dark field mask. Okay, boleh elaborate sikit, Raihan? Why did you choose negative resist and dark field mask? You boleh unmute yourself, you boleh cakap je. Type lambat sikit. Kita discuss ya, right? So you're proposing dark field. Yep, go ahead.
I think because if we use a negative photoresist, more small hole can, the mask can have a more small hole.
Okay.
More surface cover with.
Okay, so you are saying negative resist and dark field mask. Dark field mask maksudnya banyak area transparent ke, banyak area opaque?
Banyak transparent.
Transparent or opaque on the mask?
Opaque.
Opaque. Then you have holes.
Yeah.
Okay, so you explain a little bit on bila light masuk kat hole tu, what's going to happen to the resist?
Bila light masuk, so surface yang UV holes, UV direct to the holes.
Okay.
And then the carbon or under oxide under the holes doesn't dissolve.
Okay, in the holes area.
Yeah.
Okay, so light passing through the hole and the areas around the holes will not be dissolved.
Yeah.
All right, thank you. Thank you, Raihan. Right, any other suggestion? Tadi Raihan cakap negative resist and dark field mask. Okay, let's hear another one. How about... Yeah, I see one. Hold on. Faris. Faris, any ideas? Faris, anything? How do you want to frame this? Similar dengan Mimi juga. Okay, alright Mimi Okay, similar dengan Mimi. Arisha sama. Ni jawapan betul ke jawapan selamat Betul lah? Okay, okay, right. Hadi, anything? Hadi? Or anyone with different opinion that can do the same thing, maybe? Izzati. Izzati ada? Izzati Syairah. Izzati? Let's hear one more, if there is anything different. Ada ke Izzati? Go. Go, anything, go. Senyap ya semua ni. Semua setuju dengan Mimi ya? Alia, Alia, anything different? Not Alia? Anything different? Anyone at all? Anything different? Semua setuju je kan dengan Mimi? Ada yang tak setuju tak? Senyap tanda setuju lah Setuju juga? Okay, right. Okay, so yes, that can be done. So in this case, we can use negative resist and dark field. Okay, dark field mask. So negative resist here means the exposed area. Ingat dark field mask, negative resist. Saya tulis sikit, negative resist combined with dark field mask. Dark field. So means what? Your mask will be having more of opaque. Saya ambil 4 lubang ya, contoh So this is whole opaque area. Only the holes will be exposed, right? So the holes will be exposed, and since this is a negative resist, the exposed area will be apa? Negative resist. Exposed area will be, what's the word? Sebab semua setuju dengan Mimi kan? Aliyah lah, saya tanya Aliyah lah. Exposed area will be, what's the word? Yes, that's the word, hardened, right? So the exposed area will be hardened due to cross polymerization of the polymer. Okay, resist is a polymer, light sensitive polymeric compound. So there'll be cross polymerization, making the structure stronger, and therefore it will not be soluble in the next process that we call developer or removal of the resist. So as a result, you're gonna get this nano pillars. Kalau tengok dari tepi, it's gonna look something like that. So those are the pillars left after the CED process. So originally it was something like this. Originally, semua ni resist, but then these areas are not exposed. Not exposed. Therefore, they will be soluble during the development step. Okay, so tinggallah pilih aja, right? So clear? Okay, I think it's quite clear cut in this case. We discussed this one briefly when we talk about the positive and negative resist last week. Specifically when we discussed the holes formation of holes after the CD process, but this is just the very opposite of what you can do with holes, right? So the most important thing here is you need to know the mechanism, just like what I said last week. Positive resist exposed will be soluble, negative resist exposed will be hardened. And then you have to know your clear field or dark field mask, right? Clear field has more transparent areas and usually used for printing lines, right? On the other hand, if you use dark field, it's usually used, it has more of opaque areas and small holes in between, and it's usually used to print holes, okay? So those are the basics that you have to understand. Then you can solve any problem related to the printing. Right, so let's move on with our lecture. So I hope you understand already just now. So one of the many possible examples with resist and mask combinations, right? Share CD. Okay, let me share the CD. Right, can you see the screen? The lecture? Okay, good. Let's continue. So last week we stopped here. And we discussed that the basics of a lithography process lies in three main processes. Three main processes called CED, right? C stands for coating, E stands for exposure, and D stands for developer. These are the main three processes, but when you talk about the whole process steps, it's going to be more than three. But however, these are the main three cores of the in the process steps, right? So let's have a look at the process step. Right, altogether there are 8 process steps in the CED process. So maknanya CED ini duduk dalam 8 ni lah. CED are the main processes, but the rest are just what you need in between in order to make sure that the coated layer is okay. Coated layer is okay. Sekejap ya. Sorry ya. Okay, where was it? Yeah, CD. You can see, right? Just to confirm once again. Yeah, okay, good. Okay, altogether there are 8 steps in the CED process in lithography. First one is called vapor priming. Vapor priming is when you have a wafer. So kita start lithography process, we have oxide, right? We have oxide from the previous process. So the oxide is grown on the silicon, and now it's ready to be going through lithography process for printing features. So before we do the coating process, you first need to coat a very thin layer of primer. Okay, primer. In this case, we use HMDS. So the full name is, dia macam glue layer yang you have to coat first before you spin photoresist. So we need to use HMDS in the form of vapor, hexamethyl disilazine. So this is HMDS. Okay, hexamethyl disilazine, HMDS. So this is the material I use to coat, right? If you, for example, if you go through your CED but you miss HMDS, so what's going to happen is the features that you printed on the wafer will not be strong. Maksudnya macam you buat structure tak ada cement lah, tak ada foundation yang strong kat bawah. Ataupun you lekat something but there's no glue or not enough glue applied before the layer. So this is the role of this process called vapor priming. So what you have to do is you have to vaporize HMDS. HMDS ni liquid. So kita akan vaporize and then send the vapor into track. I think that I discussed briefly on the track and scanner, but this one happens in the track, the first equipment. Then it's going to coat a very thin layer. Okay? So we're going to go through the process shortly. It normally takes place at around 90 degrees to 100 degrees C for 30 seconds, more or less, to coat the glue layer, or HMDS, right? So the next process will be the C. Okay, remember CED. So at this point, we need to coat photoresist, positive or negative, depending on which type is suitable for this particular process. So what you're going to do is actually dispensing of a very small amount of photoresist. Usually, ni berbeza ikut fab and berbeza ikut process and technology. When I handled last time, it was around 1 ml. So I handled this process last time, 1 ml per dispense. So you're going to have like nozzle, then that can dispense photoresist 1 ml on 8-inch wafer yang dah ada oxide. And then the moment you have dispensed the 1 ml, and then the wafer will then be spun at high RPM. So typically in the region of 3,000, 4,000 RPM for about 30 seconds to 1 minute, depending on the process. And usually the intended thickness is in the range of a couple of hundreds of nanometer, depending on what layer are you doing, what layer are you working on, okay? So we're going to learn later on in semiconductor fabrication. Last time we discussed that when you talk about EE industry, fabrication stays in the front end, right? And the back end is something on packaging, testing. But in the front end itself, dalam proses front end ni, dalam wafer fab, we also have 2 division yang besar, front end dan back end. Okay, so dalam industri yang sama, dalam Setera contoh Infineon, so we have layers which are classified as front end, and we also have layers which are classified as back end. Okay, layers yang macam front end ni, all the oxide formation, and then all the STI, shallow trench isolation, implant, doping untuk buat source drain on the MOSFET, and gate oxide, gate. So those are considered front end layers. On the other hand, back end layers, selepas kita dah ada gate, lepas you dah ada source drain, so you want to create contacts. Okay, so remember last time when we talk about MOSFET, you need to apply VG, right? Gate voltage on the gate, and then you have to bias drain and source as well, or grounded layer. So apply the right voltage to the right side, you have to have a metal contact. So metal contacts in this case onwards are classified as back-end processes dalam front-end punya fab. Okay? Remember that? Dia bukan front-end ni semua kira front-end. So kita ada proses dalam front-end yang dipanggil front-end, and we also have processes that's called back-end process. Right? So we're going to spin the resist at a couple of thousand RPM to get certain thicknesses, right? According to the layer specifications. So the next one will be soft bake, where we bake the resist at temperatures around 90 or 100 degrees C for about 30 seconds or so, depending on the process recipe. So the goal is to drive off the solvent. Bila kita dispense resist, you're going to have solvent within the resist. Okay, bila kita spin tu dah akan ada solvent yang ada on the surface, and you don't want that solvent to remain on in the layer. So that's why you have to bake the layer in order to drive off, to remove the solvent from the resist. So that will be, okay, the C here is the coating. Then we bake. Then we go to the CED, CE, exposure. So this is where you expose your patterns that you want to print. Okay, so this can be using any light that we discussed before. It can be DUV, it can be I line, it can be G line, it can be ARF, it can be down to EUV. Right? So light source that you want to use, certain wavelength. Kalau you pakai DUV, for example, then you're going to be using 248 nanometer as your exposure wavelength. So then this is the mask that you want to print on the wafer. So circuit pattern tu ada kat mask. So we're going to reduce the size due to by using projective certain projected lens in order to reduce the size, and then the patterns will be transferred to the silicon exactly as the patterns is on the mask, right? So, but before you do the exposure, you have to make sure that the wafers are aligned. Okay, remember last time we talked about notch? Ingat lagi tak notch? Kenapa kita ada notch? Why do we have notch? Let's recall when we talk about wafer preparation, I think. Yep. Anyone? Kenapa kita ada notch? NOTCH. Anyone? Kenapa pakai notch? What if you don't have a notch?
Align kan, Doktor?
Yes. You want to align. Okay. Notch tu will be considered as zero position, home position. Bila you nak run any process that requires automation, you need to know home position. Bukan you need to know lah. Robot tu kena tahu home position. Robot arm, then system itself, scanner, track, and whatever equipment selepas proses ni, semua dia kena start off with the right home position. Okay, so this notch is labeled as, or is considered as 0 degrees ataupun home position before kita rotate throughout the circumference to get back to the same point, right? So it's considered a home position. So before you expose, you have to, kalau resist tu dia masuk dalam bukan resist, wafer dia masuk dalam scanner before kita print the pattern. So dia kena buat some alignment. Okay, nanti I'm going to share with you the stage punya processing sebelum kita expose. So dia akan buat some alignment. We call it global alignment usually. In fact, so dia akan cari home position. Bila dia fix home position, let's say this is the notch kat bawah ni, then the fix home position, then only can print the vertical pattern macam ni, this matrix. So just imagine if you don't have notch alignment, dia tak boleh align, then wafer you akan masuk at any theta, right? Dia akan masuk at any theta. Maknanya bila you print your current layer on top of previous layers, katalah you ada litho, satu device probably have like 50 times masking process, depending on technology complexity. Katalah you dah ada previous layers yang dah run for like half month or so, and then you nak print the current layer on top of the previous layers. So you want to make sure that the current layer is perfectly aligned on the previous layers. So kalau macam ni, then macam ni lah. So you have to make sure that it's perfectly aligned. So if it's not perfectly aligned, then you might end up like that. You punya layer, then you print macam ni. You akan jadi diagonal printing lah. Dia akan jadi theta ni. We're going to see later on how or where do we characterize the alignment. we're gonna have the metrology, remember? The measurement side after the measurement steps after the fabrication. So after the CED, kita akan measure dia punya overlay ataupun alignment, right? So that's why you have to align first. Okay, so that is pretty much the E exposure. Okay, so number 5 is called PEB, post exposure bake. So you want to make sure that the image at this point you dah print tau. At this point you dah print dah image dalam resist, but then you don't have features yet. So kalau you tengok cross section macam tadi tu, kalau kita discussion tadi tu, so you probably have you already have something like this already. Katalah you nak eventually you want to keep this as your features, yang merah ni yang label shade shaded region. Tapi yang unshaded region pun still there. Maknanya kita print image tu dia still ada dalam resist. It's not removed yet. So it's called latent image. Latent. Dia ada dah dalam tu tapi kita tak remove lagi layer yang soluble tu. Tapi image dah ada. Kita dah print dah sebab kita dah expose dia kan. So you want to make sure that these layers, the image and the structure that we'll end up with will be strong. Okay. Then comes the D. Develop. CED, remember? CED. C-E-D. Develop. Develop here means you want to remove the areas that are soluble after the exposure. Tak kira lah you pakai positive resist ke, negative resist ke, dark field ke, clear field ke. Bottom line, areas that are supposed to be soluble need to be removed from the resist. Okay? So develop. So in this development process, we use TEMA. Tetramethyl ammonium hydroxide. You can search online later on. So it's a form of alkaline solution. Tetramethyl panjang pula ammonium hydroxide. TEMA hydroxide. Okay, TEMA, tetramethyl ammonium hydroxide, and it's going to remove the soluble areas. And the hardened areas, for example, ataupun area yang tak soluble, will not be removed. So as a result, you're going to be left with features printed already. Okay, so maksudnya kalau you go back to this, then you're going to be left with yang ni sajalah. You akan ada feature, setelah you redraw this, you're going to end up with this only. And nothing on the sides because they are already removed by the developer. Okay. Then the next step is called hard bake. So bila dah ada features printed already, yang tak soluble tadi, yang soluble pun kita dah remove, you want to make sure that the features are strong. Okay. And you want to drive off the solvent from the TEMA development process as well. So we call that as hard bake. So bila kita dah habis hard bake, then the CED process is considered complete. And then we have to go for visual inspection, called VI. Ataupun develop inspect, sama je lah. So you can call it VI or develop inspect to make sure that whatever you print, whatever you intended to print is already printed as desired. Okay. So remember, CED is the main steps. However, you have a couple of steps before and after to make sure that the whole processes are done correctly. Right. So let's have a look at the equipments that we're going to use for this CED process. CED. So the one on the left is called track. The one on the right is called scanner. Track ni banyak jenis lah. So the one that we used last time is called is from TEL, Tokyo Electron Limited from Japan. And then the one that we use in Silterra last time, I think still now same thing, is from ASML from the Netherlands, right? ASML. So if you want to relate to the CED process, C takes place in track, E takes place in scanner, D comes back in track. So dia akan masuk track for coating, then go for exposure in scanner, comes back for a development in track, and then you're going to complete. So if you want to imagine the process, wafers will be loaded here. Okay, if you load wafer akan load, then there's going to be robot arms everywhere picking up. So station dia akan ikut module lah, one by one. So then we're going to go for priming first. Remember HMDS, And then you're going to go for coating, number 2. Then you're going to go to soft bake, number 3. So after you bake, every single time you bake, it's going to be cool process after that, right? Cool plate. So lepas bake ni you akan ada cool plate process. They can cool down to ambient temperature, then only you move on to the next step. Okay. Number 3 is soft bake, then alignment and exposure. And then dia akan masuk ke sana. Ini scanner kat sini ya. Scanner. It'll be aligned here beforehand and then exposed. And then dia akan come back for PEB hot plate juga. So PEB will be on the hot plate. That label kat sini. Then it's going to be cooled down again. Then you have to go for developer for timah. Okay, timah punya resist removal. And then you're going to go for hard bake. Then it's going to complete. It'll come back to the loader station. Okay. Then the CED process is completed. So track and scanner. So this is how it looks like. Track dekat Setera yang saya jaga last time, exactly like this. Arc 8. Tel Arc 8. This is one, most of the model that Setera has. So just to illustrate to you, here is the coating module. Ini coating, coating, C. This one semua developer. We call this cup. Ada cup macam cawan lah dalam tu. Dia module macam ni. You tengok on the right. So this is the coater cup. Yang tengok kat sini ni. Coater cup. So kalau nak buat maintenance, you have to clean this resist. You tengok kat sini dalam gambar on the right, there's a robot arm coming. Robot arm macam tu bentuk dia. Bentuk apa U shape. So dia coming. Sekarang tak ada wafer lah. So this is the robot arm coming. Bentuk macam tu. Then this is the vacuum chuck. So wafers will be placed on the vacuum chuck, and then the vacuum will be turned on. Chuck akan turun, then they can spin at a couple of thousand RPM. Okay, so before that, resist akan dispense dulu. Then we're gonna spin at a couple of thousand RPM depending on the process recipe. Then the resist is coated. Okay, then robot arm akan masuk balik, ambil ambil wafer, bawa keluar, and move on to the next process. So this is how a photoresist looks like. Kat bawah ni, cumanya in this case it's manually dispensed dengan guna tangan. Tapi dalam equipment it's not. You're gonna have like dispenser coming here, down here, nozzle dispensing 1 ml of resist before we start spinning. Cuma nak tunjuk kat you dia punya colour je lah. Okay, that's how it looks like, and this lap scale lah untuk bawah ni, so that you can appreciate how it looks like. Lap scale. Kalau lap kita sebenarnya tuang je resist tu, then we start spinning at a certain RPM. So this is how on the right hot plate looks like. So what do you think if you look at this hot plate? What do you think is the 3 hole here? Agak 3 hole tu apa benda? Any ideas? Siapa nak teka? Ada apa 3 hole tu? Anyone? So robot tu dia akan, robot ni, robot arm ni, we call it PRA, process robot arm. Tapi dalam robot arm ni, just to show you the complexity of the robot itself, automation. Untuk R8 system ni, dia ada proses robot arm, dia ada 2 proses robot arm kat tengah. Setiap robot arm, dia ada macam vertical punya system. Dalam tu ada robot arm. And for every robot arm, there are 3 pin set. Pin set ni macam yang U-shape thing. Dia ada 3 lah, 3. Satu atas, satu tengah, satu bawah. So dia macam atas, bawah pun boleh pi, tengah pun boleh pi. So memang very complex lah. So ada yang, ada certain, we call this as pin set. Pin set. Setiap satu tu pin set. Tapi sebenarnya dia robot arm lah. Ini the actual scenario in the fab. Sebab dulu saya start jaga equipment ni. Pin set. Pin set 1, pin set 2, pin set 3. Ada 3 pin set for 1 robot arm. So kita kena buat maintenance and everything. So yeah, it's very complicated. Certain pin set is assigned for certain modules, coder, developer, and dia ada sequence dia. Sequence ni kita embed dalam proses recipe. So it's very complicated. So for example, if you talk about the hot plate down there, bila you hantar wafer guna pin set, 8 inch kan, 8 inch size, about wafer 8 inch, so pin set has to be calibrated exactly following the size of the wafer. Bila you hantar dekat hot plate ni, sebelum you letak atas hot plate tu, dia akan ada keluar 3 pin kat sini. Yang 3 lubang ni is actually 3 pin. Bila you hantar wafer, nak bagi you appreciate the process. Hantar wafer pakai robot. So pin set ni ada 3, bukan pin set, 3 pin, ada 3, dia akan keluar daripada bawah hot plate tu. Akan keluar, sambut wafer lah. Sambut wafer, so pin set masuk, pin akan atas, lepas tu robot akan letak wafer atas 3 pin, lepas tu robot akan keluar, so modul akan tutup, dia akan enclose, then barulah pin yang akan turun ke hot plate, akan rapat. Maknanya bila letak awal tu dia tak rapat atas hot plate lah, sebab dia tak boleh run proses lagi kan. Bila you dah letak wafer on the hot plate, then it's already heating already started. So tak start lagi, 3 pin akan turun, bila dia dah rapat ke hot plate ni, wafer dah rapat then only the heating starts for however duration, 30 second ke 40 second depending on the recipe, then baru di start. Okay, so then the moment the heating is completed, heating atau hot plate ataupun cool plate sama je principle ya, cuma dia satu hot satu cool lah. So the moment the heating is completed, then the 3 pin will come up again. Wafer dah habis heating, dia akan naik balik, so wafer tu akan floating in air on the 3 pin. Then module akan buka, pin set akan masuk, ambil wafer, keluar balik, 3 pin down, module tutup, then next pin set akan hantar. So that's how it works, pretty much, right? So, okay. Dapat appreciate kan? At least, just to show you the complexity of the process, you won't be able to see, okay, dapat sikit-sikit tak apalah, nanti you can look on YouTube to see how the pin set actually operates. And the pin set actually operates at very high speed. That's why kalau you buat maintenance, macam saya cerita itu, kalau interlock is not on, EMO ke interlock kat depan not on, somebody doing maintenance, somebody run the process, it could break your shoulders. Okay, kalau you buat maintenance kat belakang, suddenly they run. So it's going to move like high speed theta, ni theta, dia punya angle, then dia punya x, y, sorry, xy, I said that, which way around, z is the height, and then the theta. So the moment dia pusing theta ke nak pergi daripada satu modul ke satu modul tu, it's going to happen at a very high speed. So if there is no communication between two bodies doing the same work on the front and the back of the equipment, then it could be a disaster. Right? So that's pretty much how it works on the system. Right. This is, on the other hand, ASML scanner. Ni scanner EUV saya tunjuk ni. Ni yang besar punya EUV system, the latest one. So just imagine the size of the EUV if you compare to this guy. If you say if that guy is like 1.8 meters height, perhaps. So the EUV is like 3 something maybe by the height. So that's probably 3 to 4 meters tall. So just look at the width of the system. Mungkin lebih kurang satu size bilik tutorial kot, or at least 3/4 of BT. That's very, very big. And look at the complexity of the cabling, valve, electrical, many things. Okay. Right. So it's very, very complicated system. In fact, if you talk about semiconductor fabrication, this scanner is the most complicated system in any semiconductor fabrication. Especially if you're talking about high-end devices, macam 5 nano, 3 nano, 7 nano, 14 nano, all the new chips in our phones, tablets, laptop, right? Capable of, say, AI and many other applications, right? So this is the key. This is the heart of the system. The heart is lithography. Okay. So bila you join fab, usually people say that the heart is lithography and etching. Tapi patterning, you won't be able to get features that you want to get if you don't have lithography. So, tapi ada proses lain tak setuju lah, sebab proses lain are equally important as well. Cumanya the heart of fabrication is in lithography. Right, so that's ASML system. So if you look at this ASML scanner system for exposure, so let's look at evolution of the system from 1984 to say 2010. So in 1984, resolution was only down to about 1 micron, above 1 micron. And below 1 micron, tak boleh print. Resolution means you want to print a circuit, you want to print patterns with good quality. Okay, resolution. And then 89, we moved to past 50,000, 5,000. This is model, capable of 500 nanometer or less. And then in the 90s, we have past 550 stepper scanners capable down to 90 nano. And then twin scanner ada kat Sistera. So capable down to this, but this is not the only determining factor, ada banyak lagi. So tapi system wise kat Sistera only capable to go down to about 100 nanometer overall. Okay, and then the EUV system, so capable to less than 20 nanometer. So look at the price there in 30 years, from 1000 nanometer, 1200 nanometer to less than 20 nanometer resolution. Look at the price from less than 0.5 million euro per system, here, down to 60 million euro here. Okay, kalau you convert this to USD, current system, I think on average EUV will cost you 150 mil. Oh, sorry, terlebih pula. 150 million per piece. I've also read about system that's costing up to 300 million, high end punya, per piece, satu piece saja. So in a production line, just imagine you need to have at least 20 of those to be able to run mass production. So 150 million, 200 million each for scanner alone. So tak masuk rumah kali kalau tak ada apa. Rumah tu kalau rumah 1 juta dah boleh beli 150 biji rumah. Kalau 1 juta USD lah. So if you convert 150 million to RMs, that's like 600 million, okay, per piece. Okay, I'm just gonna stop here. Nanti kita akan continue the details of every process in our tomorrow's class. Okay. So is it okay so far? Any questions? Okay. So if you're into semiconductor fabrication, then you love optics, you want to learn more optics, you want to specialize your future into optics related job, then litho is one of the promising jobs. Cumanya dia, what it takes from you is really a lot. Okay, sebab you tengok equipment pun you dah tahu kan. Tengok cable pun you dah tahu how complex is the system. But then most of the operation is automated. Cumanya you have to understand every single thing in the chamber lah. Process steps, so basically you're not gonna know everything. Ada saya punya kawan cakap dah kerja dalam lithography in 15 years pun tak tahu semua benda lagi dekat lithography tu. Tak termasuk benda lain lithography je. Kerja 15 tahun pun tak faham semua benda lagi pasal lithography. So just imagine the breadth and the depth of knowledge in lithography alone. Okay, tak termasuk benda lain lagi, tak termasuk the whole fabrication, tak sentuh lagi tentang back-end industry. So that's just lithography alone. That's how complicated the knowledge is, the expertise is, right? So any questions so far? I hope you can appreciate at this point how interesting and complicated is the process. Ada? Right, then I'll see you tomorrow then, inshallah. Okay, bye-bye. Take care. Assalamualaikum.